Hey everyone, get ready, because today we're going deep, really deep, into the world of embedded systems. We're talking about the ARM Cortex-M0 processor.
And we're not just skimming the surface here. We're going to give you a solid understanding of what makes this little chip tick, from its architecture to how memory works within it, and even how software interacts with the hardware.
So to kick things off, can you give us a little background on ARM itself?
They're the masterminds behind the processors, the blueprint designers, you could say. ARM stands for Advanced RISC Machine, and they license these designs to other companies, which is why you find their tech just about everywhere.
So ARM doesn't actually manufacture the chips.
Exactly. They're like the architects, not the construction crew.
That makes a lot of sense, considering how widespread their processors are. Now, we're focusing on the Cortex-M0, which is part of their Cortex-M family. What makes this particular processor so special?
The Cortex-M0 is all about efficiency. Low power, low cost. It's perfect for simpler applications that still need some processing muscle. Think fitness trackers, smart thermostats, even components within cars.
Okay, so these are things that need to be energy efficient, but still have enough oomph to get the job done. Got it. Now, our notes mentioned something about the Cortex-M0 being a 32-bit RISC machine with a 3-stage pipeline. Can you break that down for us? What does that even mean?
Sure. RISC stands for Reduced Instruction Set Computing. Basically, the processor uses a smaller set of instructions, making it very efficient, especially for single-cycle operations, which, by the way, are sped up even more by that 3-stage pipeline.
Pipeline. Like plumbing.
Kind of. Think of it as a 3-step process where each stage handles a different part of an instruction. First, the instruction is fetched, then it's decoded, and finally it's executed. And the Cortex-M0 does these stages concurrently.
So it's not waiting for one stage to finish before moving to the next. That's smart.
That's the beauty of pipelining. It makes the whole process much faster.
So we've got a good handle on what makes the Cortex-M0 to tick from a high level, but what's actually happening under the hood. Our source material mentions the core, NVIC, WIC, and a bus system. What are we looking at here?
Think of it like looking under the hood of a car, but instead of an engine, we have a microcontroller. The core is the brains of the operation where all the processing takes place. Then you've got the NDIC and WIC, which stand for Nested Vectored Interrupt Controller and Wake-Up Interrupt Controller. They act like sensors, constantly on the lookout for important events.
And the bus system, that's how everything stays connected, right?
Right. It's the communication highway of the microcontroller. The Cortex-M0 uses two main types, AHB Lite and APB. The AHB Lite is the high-speed lane for crucial components, especially memory. The APB is more of a local route connecting to peripherals.
So we've got the overall architecture laid out, but how does a programmer actually interact with all this? The source material mentions something called a programmer's model.
This is where things get really interesting for those who want to write code for this thing. It's essentially how a programmer tells the processor what to do. Think of it as the dashboard and controls for the entire system.
So it's the bridge between human instructions and the microcontroller actually carrying them out.
Precisely. Now, at the heart of this model is the register bank. Imagine it like a set of 16 tiny storage units within the processor itself, labeled R0 through R15. They hold the data and instructions that the processor works with directly.
Only 16. That doesn't seem like a lot.
Remember, we're talking about a microcontroller here. It's all about efficiency. 16 32-bit registers is actually a good thing for both speed and power consumption.
Okay, that makes sense. So what kind of data do these registers hold?
Registers R0 to R12 are general purpose. They can hold pretty much anything your program needs. But then we have R13, R14, and R15, which are a bit more specialized.
Specialized? Tell me more.
These are really important for how the Cortex-M0 operates. R13, also known as the stack pointer, or SP, manages the stack, which is like a temporary storage area for your program. Then there's R14, the link register, or LR, which keeps track of where the program should return to after a function call, kind of like leaving a bookmark.
Okay, I'm starting to see how this all fits together. And R15.
That's the program counter, or PC. It keeps track of the next instruction that needs to be executed. It's the boss, making sure everything happens in order.
Like a conductor leading an orchestra.
Exactly.
You mentioned the stack earlier. Could we unpack that a bit more? Our notes say it's LIFO, which sounds a bit strange.
LIFO stands for last in, first out. Imagine a stack of plates. You can only add or remove plates from the top.
So you push data onto the stack, and you pop it off when you need it again.
You got it. And just like a stack of plates, you need to be careful not to overload it or you'll have a mess on your hands. Keeping those push and pop instructions balanced is crucial.
That's a great analogy. Now, are there any other special registers we should know about?
Yes, three more. PSR, Primask, and Control. They give you very fine-grained control over the processor's state. The PSR, or Program Status Register, holds information about the current state of execution, things like arithmetic flags. Primask, a tiny 1-bit register, acts like a master switch for interrupts, turning them on or off globally. And finally, the Control Register manages which mode the processor is running in, kind of like user accounts with different access levels.
Wow, it's incredible how much complexity is packed into these tiny processors.
It's quite impressive, isn't it? And understanding how all these registers work is key to writing good code.
Now, speaking of memory, the Cortex-M0 has access to 4 GB of address space. That might not sound like much compared to our laptops or phones, but I'm guessing it's more than enough for most embedded applications, right?
You are right. However, understanding how that memory is organized is important. It's not just one big 4 GB free-for-all.
So there's a method to the madness.
Absolutely. It's all about the memory map, but that's a topic for another time.
And we're looking forward to diving into that in our next part, where we'll unravel the mysteries of the Cortex-M0's memory map and so much more.
You were right when you said there's a method to the madness. Understanding the memory map is key, especially when it comes to writing efficient code. It's like a blueprint showing how the Cortex-M0 organizes and accesses its memory.
So it's not just one giant 4 GB free-for-all. There's structure within that space.
Absolutely. It's broken down to specific regions, each with a dedicated purpose and address. You'll have areas for the program's code, areas for data, and even regions reserved for peripherals.
So it's like zoning laws, but for memory. Each area has a specific purpose, and you can't just build a factory in a residential zone.
That's a great analogy. And remember that AHB light bus we talked about earlier? That's the primary way the processor accesses and communicates with these different memory regions.
Right, the AHB light is like the information superhighway within the microcontroller. But how does that actually work? Does the processor just shout out an address and the data magically appears?
It's a bit more structured than shouting, but you've got the right idea about addresses. When the processor needs to access a specific memory location, it sends out the address of that location on the AHB light bus.
So it's like a postal code for data.
Precisely. The memory system then knows exactly where to look for the requested data, and it's a two-way street. Once the memory system locates the data, it sends it back to the processor.
It's amazing how much is happening behind the scenes just to access a piece of data. Speaking of things happening behind the scenes, our notes also mention something about exceptions and interrupts. Those sound a bit dramatic, don't they?
They might sound dramatic, but they're crucial mechanisms for the Cortex-M0 to handle those unexpected moments. Because believe me, in the world of microcontrollers, things don't always go as planned.
So exceptions and interrupts are the Cortex-M0's way of dealing with surprises.
Exactly. Think of exceptions as internal hiccups, while interrupts are more like someone knocking at the door. An exception occurs when the processor itself encounters an error in the code it's executing.
Like if the code tries to divide by 0.
Precisely. That would trigger an exception. Now, an interrupt is different. It comes from outside the processor. It's triggered by an external event, like a signal from a peripheral device.
Okay, I see the difference. So an external event could be something like a button press on a device.
Exactly. That button press would generate an interrupt, telling the processor that something needs its attention.
So how does the processor decide which interrupt to handle first, especially when multiple things might be happening at once?
That's where the Cortex-M0's interrupt system shines. It has 32 external interrupt lines called IRQs and a very special interrupt called the non-maskable interrupt, or NMI.
32 interrupt lines plus a special one. Why so many?
It's all about flexibility and handling real-world situations. With 32 IRQs, the Cortex-M0 can handle a wide range of external events. Each peripheral can even have its own dedicated interrupt line.
Like giving each peripheral its own direct line to the processor.
You got it. This makes it easy for the processor to know where the interrupt is coming from and how to respond. Now, the NMI is special. It's like a fire alarm for the microcontroller.
A fire alarm? What makes it different from the other interrupts?
The NMI can't be ignored or disabled. It demands the processor's immediate attention no matter what. It's there for those critical events that need an immediate response, like a sudden power failure.
So it's the ultimate override, ensuring those critical events don't get lost in the noise. Okay, so we've got these exceptions for internal hiccups and interrupts for external events. What happens when one of these events actually occurs? Does the processor just drop everything?
It's not a complete shutdown, thankfully. Instead of stopping, the processor takes a detour. We call this detour an interrupt service routine, or ISR.
So it's like a special set of instructions designed to deal with a particular interrupt or exception.
Exactly. Each interrupt or exception has its own designated ISR. When an interrupt happens, the processor saves its current state, like placing a bookmark, and jumps over to the relevant ISR. Once the ISR is done, the processor goes back to its bookmark location.
It's like having a personal assistant that handles all the interruptions, allowing the processor to stay focused on the main task. That's efficient.
And that's what makes these microcontrollers so powerful. They can handle a lot. And that brings us to another important concept: software structures, like polling and interrupt-driven programming.
We have those in our notes. Can you explain the difference?
It comes down to how the software interacts with those interrupts we were just discussing. Let's start with polling. Imagine you are waiting for an important email. With polling, you'd constantly refresh your inbox, even if there's nothing there most of the time.
That doesn't sound very efficient.
You're right, it's not. Polling can be a real resource hog. Now imagine the alternative, an interrupt. Instead of constantly checking, you just go about your day and wait for your inbox to notify you when that email arrives. That's interrupt-driven programming in action.
So interrupt-driven programming is all about efficiency.
Exactly. It allows the processor to focus on other tasks instead of constantly checking for events that might rarely happen. This is especially crucial for real-time systems where timing is everything.
It sounds like interrupt-driven programming is the way to go for most applications then.
It's usually the better choice, especially for complex systems, but polling still has its place in very simple applications or where predictable timing is absolutely critical.
Okay, that makes sense. It seems like we've covered a lot of ground in this deep dive. From memory maps and the AHB light bus to exceptions, interrupts, and different programming paradigms, it's been quite a journey.
And we're not done yet. We've still got more to explore in the world of Cortex-M0 software development.
Stay tuned for our next part, where we'll delve even deeper into the world of coding for this tiny but mighty processor. We're back and ready to breathe some life into these Cortex-M0 chips with code. But where do we even begin with software development for embedded systems? It seems like a whole different world compared to, say, building an app for your phone.
You're right, it is different. With embedded systems, we're working directly with the hardware. We often have limited resources and need to make sure things are super reliable.
It's not like our computers and phones with tons of memory and processing power. So where do you start? Our notes mention something called a real-time operating system, or RTOS. What's that all about?
Good point. For simpler projects, you can sometimes get away with writing what we call bare metal code, working directly with the hardware without an operating system. But when things get more complex, especially if you need precise timing or have to handle multiple tasks at once, that's when an RTOS becomes essential.
Okay, so it sounds like an RTOS is a bit like a tiny version of Windows or Linux, but for microcontrollers.
That's a good way to think about it. An RTOS is like a manager for all the microcontroller's resources. It helps schedule tasks, manage communication between different parts of your code, and make sure everything happens in the right order.
So instead of having one big chunk of code trying to do everything, you can break it down into smaller, more manageable tasks, and the RTOS helps organize it all.
Exactly. This is super important for real-time systems where timing is critical. Imagine a medical device where precise timing is literally a matter of life or death.
Wow, that's a powerful example. So an RTOS helps ensure that those critical tasks happen exactly when they need to, regardless of what else is going on.
Precisely. And it allows you to build more complex applications, which is essential as embedded systems become more and more sophisticated.
That makes sense.
Yeah.
Now, shifting gears a bit, let's talk about input-output, or I/O, programming. This is all about how the Cortex-M0 interacts with the real world, right? Making LEDs blink, motor spin, that kind of thing.
Exactly. It's how you connect your microcontroller to sensors, actuators, displays, anything it needs to sense or control in the physical world.
So how does the Cortex-M0 actually talk to all these different devices? Does it have special instructions for each one?
You might think so, but it's actually much more elegant. The Cortex-M0 uses a system called memory-mapped I/O.
Memory-mapped I/O. So it accesses things like sensors and motors as if they were locations in memory.
You got it. Each peripheral connected to the Cortex-M0 is assigned its own unique memory address range. To control that device, you write to those memory addresses just like you'd write data to regular memory.
That's a really clever way to simplify things. It creates a unified way to interact with all those different components.
Yeah.
So if I wanted to turn on an LED, for instance, I would write a specific value to the memory address associated with that LED's control register.
Exactly. It's like flipping a switch, but instead of a physical switch, you're changing a value in memory. And the best part is, you usually don't even have to work with the raw memory addresses directly. Most microcontroller vendors provide software libraries that make this much easier.
That's great for those of us just starting out. It sounds like while embedded systems programming has its challenges, there are tools available to help make it more approachable.
Absolutely. It's a fascinating field, and the Cortex-M0 is a great way to jump in. But remember, we've just scratched the surface here. There's a whole universe of knowledge to explore in the world of embedded systems.
Well, from registers and pipelines to interrupts, memory maps, and even controlling real-world devices, we've certainly covered a lot of ground in this deep dive into the ARM Cortex-M0 processor.
We've peeled back the layers and seen how this tiny chip, through this intricate dance of hardware and software, powers so many of the devices we use every day.
It's truly remarkable. And to all our listeners, especially those of you just starting your journey into the world of computer science and engineering, I hope this deep dive has sparked your curiosity and given you a glimpse into the incredible things you can create with little ingenuity and a whole lot of code. Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible.
See you in the next deep dive.